Okay. All right. So we'll just go ahead and get started then anyway. So hello to you all here today. So many in this group. It's nice to see you all for day 2 of Quantum Week, put on by the Quantum Science Engineering Center here in Mason. And today is going to be. So today our talks are going to focus on understanding quantum materials and understanding how those materials can be applied. And so we'll have some incoherent babbling from me for a couple minutes here at the start of it. Then we'll hear from Professor Tyrel McQueen from Johns Hopkins, followed up by Cho-Hee Cho from NASA, and then some of our Mason faculty giving short updates on the kind of work they're doing here, and then some Mason students, so you can see a little bit about what your colleagues and your peers are doing here. And that can help you figure out how you can get involved in it too. And then finally, at the end of this all, we'll have a quantum career panel. So you can meet some of our students who've gone to positions, at companies such as MITRE. Michael's not a student, but he came from industry, the quantum industry, into academia. And hear a little bit about, how they got interested in this and what skills they needed to succeed in their transition into this industry. So that's our plan for today. And so of the 4 main areas I told you about today, we're going to just focus on 2 of them today. We're going to focus on quantum materials and quantum sensing. And in both of these cases, the idea is to either start with a material that hosts robust quantum mechanical properties itself, or modify one in such a way to induce it via quantum confinement, and take advantage of those behaviors to make new types of technology. And so just as a quick aside, I won't go into any of the actual formula here, but just for those of you who are familiar with this, I want to put, who are not quite familiar with this, I want to touch on these 2 different kinds of things. Size engineering, or otherwise known as nanoscience, and actual quantum materials here, just very briefly. And so the main point is that if you have a solid and you shrink it down small enough, then your electrons act more like confined waves than they do particles. And so what you can actually do is tune the available energy states for an electron in a material. And you can see this really, and you can do this in different dimensionalities, right? You can start with a large chunk of crystal, you can thin it down to a very thin slat that makes your electrons behave 2-dimensionally. You can thin it down to a wire, they're 1D, and if you go in all 3 dimensions, it behaves something like as a fully confined electron, kind of similar to an electron stuck in the atom. And the size scale for this typically, depends on the material, but we're talking about making things small, like 7 nanometers is a good example for indium arsenide, in terms of how small you can go. Okay, and so this is most visibly evident when you look at something called quantum dots, cadmium selenide quantum dots here. Each one of these vials contains CAD cell dots with a different diameter, and as you can see under UV illumination, they all glow different colors. This has to do with the fact that the spacing between the energy levels in these crystals are getting smaller as the crystals themselves get bigger. And so by taking advantage of the size engineering, you can do really interesting things and kind of customize the properties of your materials. The other things we're going to talk about today are quantum materials, which are materials with properties that you can't really understand using single particle physics. And so the way I like to think about it is in terms of flocking or schooling of fish. So if you have one bird, right, it is a good bird, he's sitting right there, right, and he has certain things he wants to do. He wants to live and not get eaten, and he wants to eat things. So safety for that bird exists when there are many of them together, fighting with each other. But as they're flying around, an individual bird wants to fly close enough to his friend so he doesn't get picked off by a hawk, but not so close that he compromises his own flight abilities. And so you have these competing attractive and repulsive interactions between the birds that give rise to this collective behavior of flocking of these creatures. And so the same sort of things can happen when you put electrons in materials. Well, they're already there, but you get my meaning here. With electrons in materials and you crank up the interactions between them, you can have emergent behaviors occur that are very different from the behavior of an individual electron. And so I'm illustrating here an image of something called the charged density wave in niobium selenide, where what happens is that when you go low enough in temperature, the electrons spontaneously regroup in a manner such that they have a new pattern relative to the positions of the atom, which are all of these spots here. So the whiteness tells you how much charge you have in the different regions. And there are a lot of things like this. Every new quantum material we find has new and unexpected behavior. It's very important for computing. And there are many different kinds of effects for that here. And so Tyrel is going to be telling us today, Professor McQueen is going to be telling us today about his group's work in quantum materials. Professor McQueen is from Hopkins University. He's a full professor there. Been there since, goodness gracious, since 2009, not that long ago at all. He went to Princeton, got his PhD in Professor Collins group over there, and has more awards than you can shake a stick at, and more professional activities than you can also shake a stick at. So I won't enumerate them here. I'll instead say we are incredibly privileged and lucky to have you here today. Thank you.
Well, thank you,
All
Patrick,
about
for the wonderful introduction and for the introduction to quantum materials. And so let's just get my slides up. So, thank you for the wonderful introduction. I guess for all the students in the audience who are coming in, you might ask a little bit about my attire, and in particular, the Hawaiian shirt. So the story here is when I became a professor a little over a decade ago, both my brothers lived in the Bay Area. And when I got my professorship, they sent me a bunch of Hawaiian shirts and said, don't become a stuffy old professor. And then I made the perhaps mistake of wearing one when teaching a general chemistry class once, just for my brothers. And then after I wore it once, the class the next time asked me why I wasn't wearing a Hawaiian shirt. And so ever since then, it's sort of become a tradition for me in most contexts to wear Hawaiian shirts while speaking or talking or giving presentations. Now, I want this to be somewhat informal in the sense that you should all feel free to speak up and ask questions. I don't like talking to blank walls. And that includes for the folks online who hopefully can ask questions to Tengu, who can relay them to me. And so just with all of that sort of as prelude, it's my great pleasure to be here. And the way I'm going to present things today is mostly from a physics perspective, maybe a materials engineering perspective. If you want to see similar content, but presented from a chemistry perspective, you can go and look at a talk I gave at ACS in March of 22. I just checked this morning. It's actually not quite public yet, but it will be soon in the next week or so. So if your passion is chemistry and you want to hear the same thing, but in chemistry language, feel free to go check that talk out. Now, another really important thing, as Patrick mentioned, I sort of have my fingers in many pies. And that's only possible because I have a wonderful team of students, undergraduates, graduate students, postdocs, and full-time research scientists who actually enable us to do the work that I'm going to tell you about today. And of course, we also need the resources to do it. And we're very fortunate to be involved in a variety of projects, both large and small, funded by a variety of public agencies and private foundations to enable us to do what we're doing. And I will call out some of these individuals as I talk about their work more specifically. But first, I'm going to give you sort of my background, or a background on quantum materials and quantum information science and engineering. Then I'm going to tell you a little vignette about one kind of quantum material that my group has worked on for a number of years now. And then I'm going to tell you a little bit about superconductors, which is sort of what I call the quintessential quantum material. It's probably the first real quantum material that's been discovered on the planet more than 100 years ago. And then I'm going to tell you, if I have time, which I never do, by the way, a little bit about frontiers of materials discovery. So first, what are quantum materials? What are quantum information science? Patrick already gave some good examples of quantum materials, but I think it's worth reminding everyone that in fact, materials are everywhere in our everyday life, right? In fact, if you think about education, it's kind of interesting that we never really talk about materials as a field in high school or middle school or elementary school, because literally everything you touch is a material, right? And so it's this interesting dichotomy where it's so embedded in everything that we do that it sort of becomes invisible, right, or almost invisible. But there's no question that advances in materials have advanced society over the years. And what's relevant to this talk is that every time you sort of do something new with the material, something interesting comes out the other end, okay? And that's true whether it's figuring out how to make little bits of half of DNA fluorescence, so you can do gene sequencing and sequence the human genome, okay? Or whether it's the discovery of something called the fractional quantum Hall effect, which is a really interesting and quantum state of matter where if you have an electron gas, make it, well, we can, the right materials, in a two-dimensional plane and you cool it to really low temperatures, really cold temperatures, right? Millikelvin temperatures, and then you apply a big magnetic field, many Tesla, then you get edge currents, and then as you change the magnetic field, you see discrete plateaus, and those discrete plateaus actually come as particular fractions of the electron charge, right? So you can build a real device where you can actually say, wow, it has this particular value of its conductance, and it's quantized in units of the electron, right? Which is kind of an amazing thing. Fundamental physics, very important. Another kind of quantum material, right, is a superconductor, which is the basis for MRIs, it's the basis for NMRs, right? And if the ability to carry an electrical current with zero resistance didn't exist, none of those things would exist. And I could go on and on and on and on. And I think in the interest of time, I'm just going to say, what do we do in materials? Well, we try to pick something that we want to do, and then we have to make the materials, measure how they behave, use that to develop models for behavior, and then use those models to make predictions, which we then go and experimentally test. And if I'm doing this at a company, then I might go around this loop very, very fast, many, many times, and discard anything that's not directly relevant to the specific thing I'm trying to achieve. The reason I'm in academia is because I like the freedom to, as we do this, follow up on the things we find that aren't what we were looking for, but is something interesting and new and novel. That's the discovery part. And so that's what we do, okay? So with respect to why quantum or what is quantum and why should we care, I think it's useful to think about the fact that, you know, materials define the ages, right? There's the Stone Age, right? Nice stone tool. Here's the Bronze Age, right? You know, when some clever person threw a copper sulfide mineral on a fire and then noticed that he got this blob of coppery colored gold copper out in the remnants of the fire, right? That, of course, led to the Bronze Age, right? And then, you know, realizing that when you took iron oxide rust from dirt in the ground and you mixed it with coke, also from the ground, and put them in the same thing, you know, heat it up with fire, that then you got this silvery metal out, which we now, of course, is iron, right? Thus was born the Iron Age. And then, of course, in the last, you know, 70 years or 50 years, depending on how you define it, you know, the ability to generate billions of structures on the head of a pin, essentially, right? Through lithography and integrated circuits, right? Many people would say that we're in the silicon age, that we're, and the reason for that is that though silicon is not the only semiconductor that's used in such devices, it is certainly the most prominent. Okay? And I guess for the students in the audience, when should you be working? The answer is always. This is a lab page from the actually the preparation of the first real transistor at Bell Labs. Notice the date, December 24th, right? 1947. So they worked on Christmas Eve. That's actually when they got it to work. It's kind of cool. That's a good Christmas present, I can tell you that. Let's see. So really, this is the question: what comes after the silicon? And there's a feeling now that in fact this quantum area is what's going to come after the silicon age. It's what's going to enable sort of our next large advance in society and technology. And the way to think about this is it's related to a broader concept called emergence, that you can get collections of objects that appear to behave greater than the sum of their parts. A human is probably a good example of this. We might understand all the biochemistry that there is to know inside a cell, and yet you still don't expect a human to come up with it, or an animal of any kind, right? So in physics and in materials, the interactions are a little bit different, but it's the same basic idea. Electrons are charged particles. They like to repel each other. Electrons are also fermions. That means that they can't occupy the same state at the same time. Okay? And those tend to push the electrons apart, right? But then counterbalancing that, there are nuclei. And the nuclei tend to want to pull the electrons together, right, from electrostatic interaction. Two very simple interactions, and yet remarkable complexity results. Right? And you would not, I think it's fair to say that you would not, if you just consider those two interactions, expect that you might be able to make a material, like the one in black up here, that when cooled with liquid nitrogen, carries an electrical current with zero resistance. It's a superconductor, and thus also exhibits the Meissner effect, which allows you to repel external fields and do things like magnetic levitation, right? I mean, at the end of the day, all the physics is encoded in these simple interactions, and yet somehow that remarkable complexity is. Okay. And so the question is, how do we harness that? There are little big questions, right? So this is, we're not astronomers. We're not asking big questions. What was the Big Bang? What's the, how did the universe form? We're asking big important questions, but they're little questions in the sense that they're not, galactic in scale, right? So what are those big little questions? Well, what are the classes of emergent electronic states that can occur? I've already given you a couple of examples, but how do we know if it's a complete set? Come on in, please, come on in. You're right. Yes, that's right, indeed. How do those states arise from the structure? In other words, based on where the atoms are, how do the states appear? And what impact do those emergent states have on the physical properties of interest? And for those of you who just came in after class, I presume, based on all the backpacks, please interrupt me. Okay, please ask questions. I don't want this to be boring in some generic sense. It doesn't do me any good. So, what do these quantum effects have on the physical properties of interest? Well, you can have changes to electrical and thermal conductivity. Superconductors that can be an example. You can have changes to magnetism and spin transport. You can have changes in how these things couple to external fields like temperature gradients. So you do something called a thermoelectric that converts temperature differences into electricity, right? Or vice versa, which is then it's called Peltier cooling. That is the same phenomenon, just in reverse. Okay? Or couples to light. So you're talking either light emitting diodes or solar cells, right? Capturing energy or releasing. How do we make things insensitive to unavoidable defects? Now, why are defects unavoidable? The answer is entropy. Entropy always wins. Materials are made at a temperature greater than 0 Kelvin, at least as far as we know. That's the only way to make a material. And if you do so, then that means if you start with a system with no defects and you add a couple defects, you gain a huge amount of entropy. And therefore, you're always going to have defects. In other words, you can never make anything 100% pure. You can never make anything 100% anything. Okay? But given that, how do we harness that to do interesting things? And of course, as Patrick mentioned, are there new kinds of sensing, computing, metrology, other things that you might, metrology perhaps being a kind of sensing, although generalize it. So what's the landscape of all this? Well, having been involved in the writing of some reports on quantum materials, this being 2 of them from the last 6 years, I guess, I will say that they follow the standard adage when writing community written reports, which is they include a little bit of everything. So if you look at the things that are listed in these reports, you will see everything. Quantum spin liquids, what that is in a minute, superconductors, heroics, quantum Hall, I mentioned the quantum Hall effect already, quantum anomalous Hall, topological, lots and lots of words here, lots of words here. Question is, are these really all quantum materials? And I would say probably not, right? I would like to offer up to you that most of these things are included in these reports because they are things the community is broadly interested in. But actually, many of these probably aren't really quantum materials in the sense of having behavior at the macroscopic scale. I can give you a chunk of it. And having behavior that you cannot understand in classical terms, okay? So, you know, the idea here, the way I'm defining a quantum material here is to think about if I throw a ball at the wall at the back of the room, I don't need to know any quantum mechanics to understand how to follow what that ball is going to do, right? Yet in the other limit, if I want to understand how a single atom behaves, I can't do it without quantum mechanics, right? I can't. So, so there's an evolution from you have to use the quantum to behave it to essentially you get emergent behavior, emergent physics where you don't need to know the quantum mechanics anymore. And the question is, the real question is, just because most materials, when I make them big, the quantum phenomena disappears, is that true for all materials? And the answer is no. And in fact, for the materials for which the answer is no, that's my definition of a quantum material. One such example is a superconductor. Okay, why is that? Well, if I take a ring of a superconductor and I get an electric current running in that ring, so this is an MRI or an NMR, okay? But if I have an electric current running through that ring, how do I understand how that behaves over time? Well, if I don't use quantum mechanics, I have a really hard time explaining why those electrons can flow around that loop forever and ever and ever and ever without losing any energy, right? And why is that? Well, it's because in a classical picture, as the electrons move around, the state of the system is changing. And because the state of the system is changing as the electron moves around, we know from our good little rules regarding perpetual motion that this shouldn't be possible, right? But how does a superconductor avoid this? Well, it avoids it by forming a coherent quantum state across the macroscopic material, which is a single thermodynamic state. So although us puny humans might think of it as electrons going in a circle to understand how you make a magnetic field, that's not really the state that's going on. And the state that's really going on, there is no change in the thermodynamic state with time. It's just the phase of the superconductor, of the wave function of the electrons there is such that if I were to try to map it to electrons moving, it looks like electrons moving. But it's really just a single quantum state. Okay, so let's do this non-trivial thing. Yeah.
This is very interesting. So what do we call magnetism, right? Ferromagnet, simple ferromagnet.
Sure.
So it has to have these quantum mechanics involved, otherwise you won't get extended interaction. And it's a macroscope.
Right.
In that sense, how do you define it?
Yeah, so it's a good question. So if you think like a fridge magnet, which is a ferromagnet, it has a net magnetic field. To understand the microscopic origin of the magnetism, I, of course, need quantum mechanics to do so. But to actually explain the phenomenology of the magnetism, I don't need the quantum mechanics. And that's where a superconductor is distinct and other quantum materials are distinct. Yeah, I mean, that's what you end up having to do, right? Indeed. And again, right, so just to be clear, when you have a ring of a superconductor, the reason it doesn't violate perpetual motion is there's no change in thermodynamic state. But that's not a conclusion you can obviously reach unless you explicitly consider the quantum mechanics.
Which, I guess I think we were to look at the
Yeah.
Behavior. You say you trying to specifically say that you're preserving certain quantum behavior or all?
Formally, it would be, so the formal definition is the phenomena requires you to know something about the phase of the wave function in order to explain it. And that comes from this idea that a wave function in quantum mechanics, that observables are related essentially to the wave function squared. And the fact that observables are related to wave function squared is a very high level coarse, not exact, but good enough for us way of thinking about why when we make things big, we don't have to consider the quantum mechanics anymore, because it becomes an observable, simple observable. But for some of these behaviors, we need to know about the phase of the wave function. And that's really what quantum material is. And then the rest of everything I've just said is just sort of gross analogies. What does that practically mean for different kinds of behavior? Because that's the way I would define it. But again, there are 2 reports that define it as basically everything in materials. So choose how you would like. So what are the things you can do with quantum materials or materials more generally? Actually, this is where magnetism is a really good analogy. Is something that sort of predates, but sort of has led to what is known as quantum materials, is this idea that in fundamental physics, you can write down models of the universe and predict all kinds of funny particles, okay? Some that then turn out to be real and some that then turn out to, as far as we know, are not real. So an example of a real particle that was predicted before it was discovered was antiparticles, right? So positron, right? Or a neutron, right? Both of those were predicted, those are things that absolutely exist in real life, but they were predicted to exist before, you know, they were actually discovered, right? On the other hand, there are particles like axions, for example, or magnetic monopoles, and if this is all Greek, that's okay. The reason you haven't heard of these things, at least in a broad sense, is they're not, as far as we know, they don't exist in real life, right? But just because they don't exist in real life doesn't mean that you can't have a material that, because of the ways the particles that do exist interact, you get behavior that is identical to having that particle, right? So that's kind of that's an interesting idea. The idea is, okay, it doesn't exist in real life, but particles that do exist, with the right interactions between them, behave or formally follow the same equations of motion as though they were this other thing. And there are examples, for example, from many years ago, of materials where the excitations behave just like magnetic monopoles, okay? And there were then fancy journal articles that said something to the effect of, you know, here's a material with magnetic monopoles, right? But what's really being said there is that formally the language here is the quasi-particles, that the sort of the effective way to think about the system was behaving as though it was a collection of magnetic monopoles. Well, here's another example, and I'm sorry that the Zoom part is covering up my titles here. But this material, cobalt niobate, cobalt 2+ is magnetic, so it has a spin, okay? Now that spin is what's called an Ising spin. That means it gets to point along 2 directions. It doesn't get to point anywhere in space. The spin either points up or points down. It doesn't get to point anywhere else. This then forms these 1D lines, okay? What we found with my colleague Peter Armitage, I guess 8 years ago now, was that there was a whole hierarchy of magnetic excitations in this material. So the magnetic ground state is each individual chain is ferromagnetic. All the spins point the same way. But then adjacent chains point the opposite direction. When you come in with light and you flip one of the spins, so it goes from down to up. Well, now it turns out that now you have what are called 2 domain walls, because it's all down, then it's up, and then it's down again. So there's a domain wall because you went down to up, and there's a domain wall because you have up to down. Well, it turns out those 2 domain walls can now separate. Because after all, now if I flip a second one, well, now there's still only 2 domain walls. So the question is, what's the energy of that process? And it turns out that energy essentially scales linearly with the length of the chain. So these domain wall objects turn out to follow the same Hamiltonian, the same equations of motion, as mesons. So, in particular, bound mesons. So a meson is a real particle, right? But here we've created a material whose behavior is as though it's mesons that are bound in a linear confining potential. Okay, so it's an example of this. This was actually, they're a real particle, but we can make a synthetic version of the real particle in a material. right? Which is kind of cool. And I think in the interest of time, I'm going to skip over that. Yeah.
So you're saying that the spins change, so like if one spin is up,
Yeah.
all the ones around it will flip down.
I'm not necessarily, well, no, what I'm saying, there's an initial excitation. So you have to provide energy, right, to flip the spin. That initial energy comes from a photon.
Yeah.
Okay, so now you flip one spin. Now the question is, what happens if I want to flip the neighboring spin to point the same direction? How much energy does that cost?
Oh, wait, that's a little bit more.
And it turns out it's just a little bit. And in fact, it's linear in the length of how many you flipped. Which is kind of cool. Yeah.
Yes.
So you need to give me a warning when I'm like 3 minutes. I got it. Okay, good. That's a good question. It's a great question. So, so that's an example of interesting things that happen with quantum materials. Sort of entirely in parallel with that area was this whole field of quantum information science. And I have on my bookshelf a book entitled Physics of Quantum Electronics. And you'll notice from the quality of my scan that this is not a new book, right? In fact, this is quite an old book, right? And so what actually did quantum mechanics mean at the time this book was published? And the answer is a laser. In fact, that book is from just a few years after the invention of a laser. And if you think about how a laser operates, the only way to understand how lasing occurs is to explicitly consider quantum mechanics, and in particular, to explicitly consider phase coherence within the active component of the laser. And so this then gave rise to this whole idea of, can you have like sets of lasers and couple the phase of the photons in one to the phase of the photons in the other, right? Because they're phase coherent. Can you then manipulate those? Okay. That led to this field, which we now know as quantum information and quantum information science engineering, when it was coupled with a variety of theoretical advances. So I think many of you may be familiar with one of the original sort of proposers of quantum computing was Richard Feynman. And his vision for what you could do with a quantum computer is to simulate things like the cobalt niobate I showed you, so that we could actually predict how things would actually behave, because actually solving the full quantum mechanics directly is too challenging. Okay. But also, something that distinguishes the quantum world from, for example, the digital world that we know today is the unclonability, right? So I guess I probably show my age, but I remember days of things like Napster. How many of you know what Napster is? Yeah, I can tell age, kind of. Okay, right? This idea that, right, I mean, this is, of course, part of why computing has transformed society, right? Is that making the first one is hard, but then making copies is trivial, right? You can make sort of infinite number of copies. One of the cool things that you can prove is for quantum states that, in fact, if you try to make a copy, either you don't succeed in making the copy, or you make a copy of the quantum state, but then the original one is destroyed. So this is the so-called quantum no-cloning theorem. And it is sort of one of the fundamental limits on what one can and cannot do with quantum devices. So it can be a strength, right? I mean, at some level, that's kind of nice. That means it can either be here, I can move quantum information from here to there, and once it's over here, I know it can't be over here, right? Well, that sort of brings back the uncopyability that existed prior to most of the digital age in some sense, right? So that can be a strength, right? If you're trying to move sensitive information, for example. But it can also be a detriment, right? In the sense of it does put a limit on what you're able to do. So this field sort of grew up in parallel, okay, with quantum materials. And what's amazing is, of course, in the last 5 years, it's attracted a lot of interest, and that's, I think, why many of you are here today, right? It's attracted a lot of interest in a variety of different contexts, okay, including stuff from the Department of Defense. So that the way this saying goes is the NSA, National Security Agency, invested in a little bit in quantum computing some number of years ago, and they didn't really think it was going to work, but you got to be speculative sometimes. And then they moved a bunch of stuff to a classified side of the fence, and that was taken as an indication that, oh, maybe it will one day work, right? And so that then, of course, led to a variety of things, including national investments in quantum information science. So there was the National Quantum Initiative Act passed by Congress a couple of years ago, right, that explicitly directs a large amount of funding in this area. And it's because the expectation is that the ability to harness these quantum phenomena is going to lead to our next revolution. And it's also led to a variety of public and not so public conflicts of what does it mean for a quantum computer to beat classical computers or vice versa. Okay, this is just, I don't want to get into that debate, okay? As someone who has friends and colleagues at both Google and IBM, for example, quantum area, I don't want to get into the debate, but the point is this question of, there are certainly problems that quantum computers should be able to solve that classical computers struggle with. Okay?
So I guess like this kind of business question. Normally, like more of a scale systems.
Yes.
And given the whole deposit is kind of the only way, like it would be.
Ooh, that's a good question. Can photolithography be used on quantum materials? Well, the short answer is yes. Longer answer is it's already done. Even longer answer is many of the quantum computing platforms today, including the ones both Google and IBM, are based on what are called superconducting qubits. And those you actually do define with photolithography. Now, it turns out one of the there are effects from interfaces in particular, for example, that cause decoherence, which limits the sort of the effectiveness of those qubits. And those limits come down to limitations in photolithography. Okay, and understanding those limits is absolutely a big open area of research, because if you can tackle that, you can make qubits that are much higher fidelity, that last a lot longer, which means you can build bigger systems, solve more challenging problems. You're right, photolithography isn't going anywhere. But this puts a new spin, perhaps pun intended there, on what's required in terms of the chemistry, especially in the interfaces, to actually do interesting things. So my point is that actually these two areas are converging at a remarkable rate, right? So there's already some demonstrations of the vision of Richard Feynman and others, right, of actually simulating real systems with quantum computers, right? So Hartree-Fock, for those of you who aren't chemists, is a classic electronic structure approach to understanding molecular systems. And here is actual systems with, 6 to 12 qubits actually simulating a very small molecular system using Hartree-Fock, but not using classical computing, but using supercomputing, or using quantum computing. Okay. That's an example of the quantum computing informing the materials, right? Or in that case, a molecule. The converse is, okay, I mentioned photolithography here. Here's a bunch of photolithography devices. And in particular, finding better materials that more ideally reach the limits of what are possible from quantum coherence, because at the end of the day, it's the phase of the wave function that's all important, and decoherence is essentially the loss of the phase information, okay? So finding materials where you can preserve that phase information for as long as possible and manipulate it, move it around and everything else, that's the name of the game. And given the current state-of-the-art materials here are things like niobium or tantalum, which by the way are superconductors that have been known for 90 years, or things like nitrogen vacancy centers and diamond, material that's also been known for many, 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 many years. I would offer up that I can give you a lot of evidence, but just on the face of it, that probably tells you that we're not at the optimal point on the materials complexity versus performance scales. These are all very, very simple materials, and of course they're chosen because at the time when this field was growing up, they're sort of very well understood and well defined at the time. But that also means there's a lot of headroom to go further. right, to incorporate all the advances in quantum materials over the last 50 years in actually building these things. And so I'm sure I'm running out of time. I must be. I still got 5 minutes. Okay. Good. I haven't gotten any science yet. It's good. I've just given all the background. I'll skip this slide. You can go look at the reference if you're interested. The point is, all kinds of ways to make materials results in all kinds of properties, which results in all kinds of interesting applications. And it's a soup. Finally, to get a little bit about what I do. Okay, sort of more in detail. Although still at a high level. There are really two grand challenges in materials. Okay? The first is, how do we make highly structured materials? Does anyone know what this material is? Anyone have a guess? Someone must have a guess. What? Silica. Okay, that's not a bad guess. How about chalk? I get chalk a lot too. I get silica a lot. Those are the two most common answers I get. It's not. It's bone. Okay? And of course, I think as you all know, bone is actually a remarkable mechanical material, right? Because it is on the one hand quite light, but it is on the other hand quite strong, but it is also quite bendable, right? Quite flexible, sort of all contained in one. And the reason for that is because it's not a single homogeneous material. It has large structure across length scales. And photolithography, we have a great tool for doing this in 2 dimensions. How do we do that in 3 dimensions? Or how do we do it in the atomic scale in 2 dimensions? We actually don't have great ways for any of those things. Developing ways to do that is an active area of research and a place where my group tries to do some things. Okay. The second question is, how do we harness these quantum effects on a macro scale? Levitating sumo wrestlers may not be the most important thing to be doing with the quantum material, but it certainly makes the point, right? That there are things you can do with these that you can't do with them. Or if I say it a little bit less, without the graphics, how do we put every atom in its place together, right? That's an incredible technical challenge that we're certainly not going to try. So in the last 3 minutes, I think what I'd like to do is just tell you something about something called a quantum spin liquid. So a quantum spin liquid is another example of a macroscopic quantum material, if we can make it. The idea is that instead of being related to charge, like the charge of an electron, like in a superconductor, it's related to what's called the spin of the electron. So that's the magnetic moment. Spins point up or down. It turns out that there are some arrangements of atoms, such as corner-sharing triangles, known as the Kagame lattice, where if the spins energetically want to arrange themselves to be anti-parallel with each other, which is anti-ferromagnetic, that there's actually no way to do that and satisfy all the energy interaction energies, right? Because on a triangle, once one is up and the second is down, well, no matter which way I flip the third, I have an unfavorable interaction. The result of this formally is something called a degeneracy of magnetic interactions. And that degeneracy, when we cool to 0 Kelvin, remember our old friend entropy, when we cool to 0 Kelvin, something has to happen. And a quantum spin liquid basically takes all of the possible pictures of all the possible spin configurations, makes a linear combination of all of them to form a single quantum state, and makes that single quantum state lower in energy than all the others. So you satisfy the requirement that entropy goes to 0 at 0 Kelvin, but you've done this wonderful thing of coalescing all of these individual pictures. And so it gets the name quantum spin liquid because if you look at any one spin, it looks like it's flipping up again. But it has a long-range spin entanglement. And my group has spent a really, really long time developing materials for this and working with collaborators to put them in devices and photolithography and all these kinds of things. Okay. I think perhaps, yeah.
So one of the consequences of the third law is that we can't reach zero Kelvin in a finite step. So,
yes.
When you say like even at 0 Kelvin, you mean like you and your colleagues are like getting really, really close to that? zero?
That's a good question. So there's, oh yeah, so that's a great question. So the question was, you know, I said, well, even at 0 Kelvin, it looks like the spins are fluctuating up and down. What does that really mean? Because you can't get to 0 Kelvin experimentally in real life. And the answer to that question is you're right, of course. Experimentally, we can't, but we can try to get close. But I meant that statement from a theoretical perspective. Because in theory, at a theory level, we can certainly ask the question, what would it do at 0 Kelvin? And the defining feature of a quantum spin liquid is even at 0 Kelvin, because it's the single admixture state, it still looks like the spins are fluctuating. So I know I'm basically out of time, so I just want to highlight what are the new things that come out when we do this. And here's a result that you're going to see on the cover of a fancy journal in the near future, which is something called a field-free Josephson diode. So a field-free Josephson diode is, so a Josephson effect is if you have a superconductor, an insulator, and a superconductor, you might think that that insulator blocks the flow of electricity. But that's actually not the case, right? Because the wave function doesn't go to 0 at the insulator, it exponentially decays. And so when you have a finite insulator thickness, the supercurrent, the Cooper pairs, the pairs of electrons that give the superconductivity, can actually tunnel through it. Okay, and this is actually something called the Josephson effect. And I'm not going to tell you all the details about it. But normally, you build a material that looks pretty symmetric. You've got a superconductor, this insulator, which is a quantum spin liquid candidate, a superconductor, okay? And you try to run electricity through this junction. It's a diode. It passes current better one way than the other. This is entirely unexpected in most interface theory, right? Because normally, if you've got the same kind of superconductor on both sides and an insulator in the middle, it shouldn't matter the direction, right? And yet here, I mean, I'm showing some of the data here, it rectifies. So it allows current to flow more effectively, supercurrent to flow more effectively one way than the other. Okay. Turns out the origin of that is this material has a built-in electric field. It's actually polar. And that built-in electric field is what results in this asymmetry. So it actually has nothing to do with quantum spin liquid physics at all. But it's a good example of discovery, right? That by trying to connect to this quantum spin liquid state, we found something else very interesting and actually potentially technologically very useful. Okay. And that's, of course, with my collaborators in the Netherlands. Yes. It's not a transistor, it's a diode. But yes, you can envision more elaborate architectures that would allow for things like a superconducting transistor and other interesting devices that are relevant for building quantum computing devices. And a lot of this work is with a good friend of mine, Mazhar Ali, who's at Delft in the Netherlands. Okay. Yeah. So the material in the middle is ND3BR8. It's a trimerized Kagame lattice. And it does this rather remarkable thing, which is wild, indeed. And we did not expect it, right? We were trying to build these devices to try to figure out, as a first step, to try to interface with the spins in a quantum spin liquid and actually probe whether or not there is these entangled states that I was telling you about, right? And this was like the very first step in like 10 steps to get there, right? And then we find this other thing instead, and that's, I think, representative of how this all works. And so, of course, as I said, I always make my talks way too long. You can ask me about some of those slides if you're really interested. I guess for all the students in the audience, I'll just say, how do you actually discover things? You do it by looking in new places. And if you're interested in some of this stuff, one of the projects I'm involved in is something called Paradigm, platform for the accelerated realization, analysis, and discovery of interface materials. We run yearly summer schools that are in person at Cornell and Johns Hopkins that cover the materials growth, the characterization, and the theory behind a variety of behaviors. We have 2 of those summer schools coming up this summer, one in June on MPE and ARPES, and one in July and early August on quantum applications of superconductors, and I encourage you to apply. The system will say the deadline is tomorrow, but I promise you, you're going to have at least one more week to apply if you're so interested. And with that, I know I went 2 minutes over, but thank you for the time. And you are always welcome to reach out to me by email or just talk with me after this about any questions. So thank you again for the invitation. And is there a question on Q&A? Yeah. So what's the question? So that's a great question. So the question is, how can we find the most interesting questions that a quantum computer can solve? And that's actually, I'm going to make that a multi-part question, because you can ask, given quantum computers as they are today, what problems can be solvable? And then if quantum computers continue to proceed and develop into their full potential, what problems might they be able to solve? Okay. So for problems that they can solve today, actually map very nicely onto some of the things that we face in real materials. So there are different kinds of quantum computing. One kind is called quantum annealing, okay, which is a company like D-Wave, for example. And what you can do is you can imagine that when you build the largest quantum computers that you can today, they're defective, right? There are qubits that don't work right? Or have various limits. Well, it turns out that's a pretty good model then for a real material with a real defect, right? So one problem that I think quantum computers are very effective at tackling today are actually the imperfect problems. Are things that are simple models, but with the addition of defects. That actually the simple models plus the defects, that's really where quantum computers right now are going to show. Okay?
I don't know if that is a great answer. I'm not exactly sure.
Yeah, well, so then you're letting me get to the second part of my answer. The second part of my answer is, what problems might you be able to solve? And this now intersects with this whole field of computing and computing theory, and what is computable and what is not computable, and at what time scales are things computable. The thing that has the reason NSA invested money into this many, many years ago, right? And the reason places like NIST, just down the street, National Institute of Standard Technology, is running a competition right now for post-quantum cryptography, right? Cryptographic methods. The reason there was interest there is because there are a class of computing problems that are thought to be hard on classical computers. And the formal definition of hardness on a classical computer means you can't solve them in polynomial time on a classical computer, but that you can solve them in principle in polynomial time on a quantum computer. Okay? And this is important because the mathematical how shall I say this? The mathematical one-way functions that a lot of our cryptography is based off of today are problems that are not polynomial on classical computers, but would, generally speaking, be solvable in polynomial time on a quantum computer, which now means that all of the sort of the things you're trying to protect and keep secret and private all of a sudden become accessible. Okay. Now, there are some problems, though, that are hard even for quantum computers. So if I think about this like a Venn diagram, there are some problems that are hard for a classical computer. There's a smaller set of problems, but still finite set of problems that are still really hard even on a quantum computer, right? Or at best have slightly worse performance. So I don't know how detailed do you want this answer? So so if you look at something called symmetric cryptography, okay, the best symmetric cryptography algorithms that are known, quantum computers give you a square root speedup. So what that means is if it would take 2 to the 256th time, which by the way is longer than the age of the universe, right? But if it take 2 to the 256th time on a classical computer, it will take 2 to the square root of that, which is 2 to the 128th time on a quantum computer. And that's the best you can do, right? So it still scales in a hideous, horrible way. But there's a different set of problems which they're much more effective at solving, but they're not unless you want to do like 3 times 5 is 15 and factor 15, which has been done. But if you want to do more than that, it's not really there yet.
I think do we have enough time for more questions, or should we take a break and have a formal?
Yeah, you better stop here. They don't talk about this.
So how do we do this? It's break time, but feel free to keep asking me questions. So what's the question? Oh, scaling the size of quantum computers. So that's a good question. So, and this depends very much on the details of how you're building a quantum computer, right? And I guess the way I think about this is that we currently in quantum computing are in the same place that we were with computers with the vacuum tube. We have the quantum equivalent of vacuum tubes, and they work, and they'll let us get to some scale. But we need the equivalent of the integrated circuit of the transistor in quantum, and we don't have those yet. Now, to more directly answer your question, superconducting qubits, there are different varieties, but they're, at the end of the day, micron-sized devices. And you can't make them smaller because of limitations on the capacitance or the inductance, which is then what sets the frequency that you need to actually interrogate them, okay? That's in principle overcomeable, right? If you have the right kind of electronics and the right this, that, or the other, that in principle is overcomeable, okay? If you're basing it on atom systems, well, you need atom traps, and atom traps typically involve lasers, right? And lasers are pretty small these days, but you still need the vacuum chamber. And vacuum chambers you can make small, but it's still microns, you know, even if you're building it on a chip, it's still microns or larger, right? Which is really small, right? But it's actually, but it is at the same time a factor of 1,000 larger than, you know, a modern transistor. I don't think that's the key scaling issue, right? The key scaling issue is the same thing that makes solving quantum problems hard, which is it's all about the interactions, right? And if I think about a quantum annealer, if I have n qubits, I need to tailor 2 to the n interactions. Well, when n is 3, I can do that. When n is 1,000, how am I going to tailor 2 to the, you know, right? 1,000. That's really where the scaling gut problems are. Or if you want to think physical size, the cooling. Well, yeah, I mean, at some level, okay, if you make things smaller, does new phenomena emerge? And the general answer to that is yes. And specifically in quantum systems, the answer, of course, is yes, because you've actually made them real quantum objects at that point, right? But I don't know if that answers your question, but that's a great question. Just break, but feel free to keep asking questions too.
Thank you for that.
Of course.
Let's thank Tyrel. I don't think we've done that. Thank you. So these opportunities, make sure you make note of that, right? Like especially you the undergraduates looking for something.
It's also on paradigm.org, by the way, so feel free, you don't have to try to copy the slide. It's on paradigm.org. There's no G in paradigm. There's a whole story there. It was the originally platform for the accelerated discovery of interfacially grown materials, which would have the G in it. But then it then became a lowercase g subscripted on the I, and then it disappeared. So
now it's
paradigm, yeah.
Well, yeah, if you guys do want to, we can put you in touch with Professor.
Yes, of course. Again, I'm always happy to talk. My contact info was on there too, but McQueen@jhu.edu is a good email. No one ever calls me these days, so if you really want to get my attention, look up my office number and give me a call. Lightning McQueen. I don't know if you've heard me. I heard you. I did hear you. And it's funny because when I guess I didn't explain the mugshot. The mugshot that was on my front page. That was of Steve McQueen, who was a famous actor. Yes. And I sometimes get asked if I'm related to Steve McQueen. And the answer is no. But Steve McQueen's first real name was Terrence. So when he got arrested for drunk